The subject is axiomatics of exceptions, is about the exception proof rule. So we have introduction, start with introduction, and then we talk about some goto because we want to use goto to define exceptions. Along the way, we talk about axioms of goto, which is the precondition of goto. I'm not sure whether the audience understands which is the precondition. If you don't, let me know and I can explain it. And we also talk about miracle statements, which is used to represent goto labels.
Yeah, wait, Chen, your slides are not moving.
Yeah, I'm still in agenda.
No, it's still there in the first slide.
Oh, really?
First slide. Your slides are not moving.
Okay, let me see what's going on. Is it moving now?
No, it is not.
I don't know.
Can you just click that slideshow?
Yeah, I'm doing it. Yeah.
Yeah, click on slideshow.
Let me stop sharing the share. Maybe that's the sharing issue.
Okay. Yeah, your screen is not visible now.
Can you see my screen?
Yeah, your screen is visible. Yeah,
Can you see my presentation?
Yeah, you can. We can see your presentation.
So let's see whether slideshow works or not.
Yeah. Slideshow from beginning. Yeah. Can you go to the next slide? Yeah, now it's moving. You can go ahead.
All right, so it's the agenda.
Yeah.
Since we intend to use goto statement to represent so we talk about goto first. We will cover weeks of goto, axioms of goto, and proof rules of goto. We talk about proof rules for exceptions. So goto, we know that we don't like goto statement at all in our current practice. But we know that goto has a special use to represent the exceptions, to handle exceptions. And our research showed that that's indeed the case. So we are going to use goto to see how can we present the exceptions. So let's start goto. So first, we define what is the precondition of goto statement. So what is the precondition is really just statement and post condition. What's the weakest condition? That can execute the statement and guarantee termination. So for goto we'll take the execution to enable. So with the condition of execute, goto must it's labeled with the precondition. So that's why we have find the WPL, which is with the precondition at label L. There are several observations about this definition. First, whether goto reaches end or not, it really doesn't matter since we're looking for precondition. Number two is that the rule doesn't require the uniqueness, so that we can have multiple labels in a program actually, but we are not use this feature in this paper. Number three is that the rule doesn't impose any scoping, nor requires where the label should be. So actually the label can be inside of a loop body or in a relation body construct. Number four is that the rule does not satisfy Dijkstra law of excluded miracle. That means it is a miraculous statement. From this week's precondition, we can easily to formulate certain axioms for goto. One of the biggest misunderstandings is that there is no axioms can be formulated in the Hoare native proof system, which is not true. So to represent a goto statement, especially the difficult about a goto statement is about its labels. But we use auxiliary statement, so we can no longer use labels. So this statement is called a miracle Q. It's called a miracle because for it can reach anything as long as its precondition is met. So equivalently, we can use goto L to be written as a miracle WPL because their weakest precondition is the same. Similarly, we have about, okay, which is not really important for this presentation. So let's review goto proof rules done by Clinton and Hoare in 1974. So they gave this formula or proof rule. There are certain drawbacks. Goto L in S1 and S2 are syntactically incorrect because the label L has been removed. From text, we can see L is in front of S2. But the lower condition doesn't have L, so the S1 is S1 and S2. Even if it contains goto L, it's not syntactically correct. Second drawback is that goto L appears while being defined. We're defining goto L, but it appears in a lower condition. The third one is that cannot handle multiple labels while looping back conditions with looping back conditions. That means the so-called backward goto, which we are not used in this paper, but we have to mention it when we do the study. So now let's use miracle equivalence of the goto to replace the goto. We got the left side. Since Q is arbitrary predicate, we can take WPL as a Q. After the replacement Q with WPL, that means the left-hand side of sleeping T sign is just a miracle axiom, so we can remove it. So we come up with the right-hand side of the rule. Now everything is in terms of WPL, which is unknown right now, so we can use Q back to replace WPL. So this is really the left side of this rule. So this is really just a rewriting of Clinton and Hoare's rule. So now we can take S2 as a skip. So we come up with the rule on the left-hand side. So we know that S may contain goto L, and this goto L in S is called forward jumping because goto L was seen first before the label. So essentially, this new rule at the right-hand side is really just labeling. As long as we can prove this statement, that means that we can put the label at the end of the S. So in the same paper, Clinton and Hoare also define the rule of goto in a min text as exception handling. So S1 is the exception handler. The program starts with S2. If S2 level met goto L, then it will answer automatically, normally satisfying R2. If it meets goto L, it will continue from S1 and end up with R1. That means at the end, R1 or R2 will be satisfied. This is essentially what Clinton and Hoare's exception semantics. So after analysis of the S1 and S2, we can really simulate the original, bring it back to the forward goto instead of the appearance of backward goto. Let's look at this again. Because the S goto L is in S2, not in S1, so we can put S1 anywhere we want, even after S2. Right, so we come up with the simulated that this way E block first, that's the S2. Then after S2 ends normally, so we go to next statement, go to next. Or if we see goto L inside the E block, then we do exception handling, so which is similar as the Clinton and Hoare's statement. We need to derive S block the proof rule with respect to the precondition P and the postcondition R. For S block, there are two labels. One is L, one is next. Let's process next first using the rule, goto rule. Then we come up with that miracle R is replaced with goto next. And then we processing L, then we replace all the goto L with miracle R, a Q. After massaging miracle R and Q together, so it can become the post condition R, then we come up with the following exception rule. So in modern language, we don't use the goto explicitly. We use a try, raise, catch construct instead. But this construct can be simulated by goto statement. Right, so we execute E block first, then when we see exception, we raise it. With a certain parameter parsing mechanism. Then after the end, if we don't see goto L, we do goto next, and then if we see goto L, we do parameter parsing, then we do exception handling. So after massage it, we can come up with this following rules with exception, with message parameter parsing mechanism. We can tell if we don't have parameter parsing at all, if we decide to create an exception without a parameter parsing, then it actually becomes a two-proof obligation similar to the same as block the proof rule. Since Q1 and Q2 are the same without parameter parsing. So let's do some case study. I hope that I won't lose any user by doing this, but let's try it. So we are doing a table search, find a K in a two-dimensional array A. So we start with x equals A and end up with x equals A, and we have a variable called found. If there are K there, found should be set true. And x equals A in a precondition and both precondition and both condition, that means that x equals A is not changed. Then we come up with the right-hand side program, but in this program there are certain problems. First, we didn't follow invariant we come up with because we try to use a loop to determine not found, but we set the found equals to true in the middle of the program. The second is inefficient because we didn't enforce the short exit. After found, we still continue doing program. Let's improve it. So we create a found exception, and then when we reach found, we instead of assignment, we read the found and go to the exception handling block. Then actually this is very nice because the found exception will be replaced by goto statement, which is a miraculous statement. That means it can handle everything afterwards. Of course, it's invariant as well, so we don't have the problem. Invariant is not followed. It's also efficient because as soon as we find a K, we do a jump to the exception handling block. So we solve both problems. So we can easily extend this model into multiple reads catch and also include a finally block because everything can be written as a goto statement. Now, and 1D snapshot use traces to define exception semantics, which doesn't come up with proof rules as we do. King and Morgan, as well as Christian, use the actual postcondition to modify to represent exception block exit, which is much more complicated in that it violates all the current methodology.